So I'm here to present the second part of the deep learning tutorial, which is now specifically devoted to deep learning for natural language processing. And again, maybe similar to what Andrei had, I have quite a lot of time, so we will proceed rather slowly, and I will try to explain stuff along the way as we go. Through my part. And our plan for today is actually, even though we have a lot of time, it's still quite ambitious. So we will start with an introduction to distributed word representations. We'll have, hopefully we'll have a live demo about it, although I'm not really sure by now. And then we will try to start from the word embeddings, start from the distributed word representations, and go in two different directions. We can either try to go up and go from representations of a single word to representations of a sentence, a paragraph, a small chunk of text, or we can go down and we can try to recall that words are composed of individual characters, and maybe we can somehow use these characters to our advantage too. And then I will give a very, very brief overview of what is actually, how deep learning is actually used in natural language processing. And I hope that the focus here will be on the new architectures, on the new models, on the new approaches that natural language processing has introduced to deep learning. Because yes, I will mention this, in many cases you can just take a standard convolution architecture or a standard recurrent architecture, plug into this architecture a natural language problem, and get some results. We will see examples like this. But I think the more interesting part is when the motivation from natural language processing brings new techniques, brings new approaches, and leads people to develop new models in deep learning. So hopefully we will see a few examples of this. Okay, but first, just a very brief overview of what Andrei has told you, because I will just go through the most common architectures used in modern neural networks. So first is the basic feed-forward neural network, when you have several layers, and on every level, every unit is fully connected to all neurons on the previous level and all neurons on the next level, right? This is the very basic architecture that's been around for a very, very long time, and basically the difference is that now we can train it better. Autoencoders. Andrei mentioned autoencoders. It's a good way for unsupervised feature selection. You compose an architecture where you try to, where the output basically equals the input, that you try to reconstruct a copy of an input at the output, and either you have some kind of a bottleneck at the hidden layer so that you force it to have you force it to have a smaller dimension or some sparsity properties or something like that, so that at the hidden layer you will have a good, interesting representation, not just a copy of the input. Or you use what is called a denoising autoencoder, probably the most often used and the most useful kind of autoencoders, when you distort your input, you change a few things, you get some kind of random noise. What it means depends on the specific application. And then on the output layer, you try to reconstruct the original input. So again, it's still unsupervised, but now, for example, for images, you take an image, you remove, I don't know, half of the image at random places, replace pixels with zeros, and you ask the model to reconstruct them. This works very well. Then we have convolutional architectures. And again, Andrei has has had quite a few slides about convolutional architectures. I will not repeat this. But the basic idea is that we start with local feature engineering at the level of local windows in the input, and then again use local windows, but now on the pooled features from previous level of local windows and so on. So basically, on subsequent layers, we generalize more and more, and then on the last levels, we hope to have reasonable features about high-level objects. This is very often used, of course, in image processing, in signal processing, but the convolutions don't have to be two-dimensional, they can be one-dimensional, and this is exactly what usually happens with texts. Text is a string of symbols, and you can have one-dimensional convolutions on the symbols or on the words, and we will see examples of this today. Recurrent networks, I think this is exactly the same picture as Andrei has used from a very popular blog post. I sincerely recommend it. Again, the recurrent architectures are especially useful in natural language processing because they are designed to handle sequences, and text is a sequence, right? So in a recurrent architecture, your network has some kind of hidden state, and it propagates this hidden state further, changing it along the way in some way that depends on the current inputs. And it produces hidden states and outputs along the way, and then you can do something with these outputs, right? And the basic architecture is what is called just simply a recurrent neural network, RNN. But again, as Andrei has mentioned, it is not very suitable for processing sequences where there are any kind of long-term dependencies, right? Why is that? Because basically because of the problem of vanishing gradients. I guess I think this Andrei has not really explained. So since I have have you, right? You haven't explained that in detail. No. Okay. So yes. So I will say a few words because this is very, very important for the recurrent architectures. Are very important for text processing. What is the problem of vanishing gradients? Basically, you have a matrix of recurrent weights between the hidden states in this recurrent network, right? And as the hidden state is propagated forward, or which is the same as the gradient is propagated back, you keep multiplying by the vector of weights by this matrix of recurrent weights, right? And you cannot really rely that you cannot really be sure that this matrix will have a determinant of exactly 1, right? So when this determinant is larger than 1, the weights will grow, right? The vector of weights will become, the absolute values of the weights will become larger and larger, and this is an exponential process. They will just blow up, and this is known as the exploding gradients problem. And to fix the exploding gradients problem, people usually do some sort of dirty hacks like gradient clipping. Basically, you just say that, okay, the gradients can explode, but we will artificially just clip them to a maximal value, and we will not allow them to grow larger than a maximal value. Okay. But on the other hand, if the determinant is less than 1, then you have the opposite problem. You have the problem of vanishing gradients. And the in vanishing gradients, it means that the network kind of works, it kind of trains, it does something, but the influence, I will not really do a lot of mathematics here because I think I will try to relate the basic ideas, but I will not really explain them in full formal detail, okay? So the basic idea is that like the influence of the current input cannot be propagated too far because it attenuates, it becomes smaller after each multiplication of by this matrix, right? So, and very soon, again, it's an exponential process, so very soon very soon this influence of, say, x0 will just become negligible, right? And now this is a real problem. And to fix this problem, we have to change the architecture of the network, right? So now this Andrei has told you about, and again, I will not go into formal details, but I want to make one specific point here. The modern recurrent architectures are usually composed of the so-called LSTM, long short-term memory units, or GRU, gated recurrent units. And the main idea of both LSTM and GRU and all their variations is that we try to avoid this problem of vanishing gradients by having the gradients not vanish, right? By simply not having this matrix of recurrent weights that is applied to the hidden state on every step. So if you, again, I will not go through the formal details, but if you just look at how the hidden state changes from time to time in a gated recurrent unit, you will see that basically it is exactly the previous state, right? Plus something new, where the something new, whether the something new is actually replacing the state depends on this gate, and I will not explain this in detail. But the basic idea is that if you take the, yeah, I think I have it here. Okay, no matter. If you take the partial derivative of ht by ht minus 1, you get a 1. You get a 1 plus something new if the unit actually decides to replace its memory. And if it does not want to replace its memory, then the gradients will just flow through with no change. Okay. So this is the gated recurrent unit. It's a simplified version of LSTM. It was introduced. Well, the LSTM was first. The LSTM is a very, very old idea. And again, one general remark about the whole field of neural networks is that it is by the standards of machine learning, it's a very, very old field, right? The artificial neural networks were like the first formalism of machine learning. They were introduced back in the 1940s and 1950s before we even had the words like artificial intelligence or machine learning. And many of the ideas that I'm talking about now were introduced very, very early. For instance, the LSTM, okay, it's relatively late. It was thought of in mid-1990s, right? So in the works of the group of Jürgen Schmidhuber, the LSTM and similar architectures were developed from 1995 to, say, 2005. I think the final modern form of an LSTM was introduced in 2005. And this idea of having the gradient just flow through without change is quite old. And it was introduced specifically to handle this vanishing gradients problem. So again, these are very old ideas, but now we have both the data sets and the hardware and the possibility to compose these old ideas in new ways so that now they actually start to work. Okay, so the difference, the deep learning revolution that happened 10 years ago and has been happening since is, I mean, at least as much about the size of the data sets and the hardware as it is about the new ideas. Okay, so if you take a very old neural network architecture from the 1990s and you just make it larger and you train it on modern GPUs, you will get a very reasonable network. Sure, people have introduced new stuff. Sure, we have new regularization, we have dropout. This is like a very important new idea. But and we have batch normalization and many other tricks. But basically, the basic architectures have been with us for a long time. Only now we have the opportunity, we have both the hardware and the data to train them. I want you just to maybe have this as a takeaway point from my presentation. Okay, so, and these were like the basic, most often used architectures of neural networks, right? Just feed-forward, convolutional, and recurrent. And recurrent are usually done in the form of LSTMs. And when we say deep learning, we basically just mean that there are several layers of this stuff. Okay, so when we speak of a deep feed-forward network, it just means that there are several hidden layers. When we talk about convolutional networks, they are deep almost by definition. They have to have several layers, otherwise they are just useless. And when we speak about recurrent networks, whether they're just simple recurrent networks or they're composed of LSTMs, deep just means that the outputs of the first layer serve as inputs for the second layer, and so on and so forth. So like the second layer attempts to capture patterns in the sequences of patterns captured by the first layer, and so on. And again, the idea, the hope here is that further layers will hopefully capture some higher level dependencies, which would be, of course, very important for text, because text is a very, very, very complicated thing, right? Okay, so this was the introduction, just an intro to deep learning. Probably I have repeated Andrei a lot of times. And now let's proceed to specifically text mining and text understanding. The first important idea here are the distributed word representations. The distributed word representations are based on what linguists call the distributional hypothesis. And I think you know about this better than I do, but the basic idea is simple. The idea is that a word is defined by the contexts in which it appears, right? So, for instance, when we humans learn a new word, very seldom we go and look it up in the dictionary. How often do you do that? I know that I basically never do that. When you learn a new word, you see it in a few contexts, and maybe, for instance, you Google it. When you Google it, you see it in a few other contexts, right? And then you just derive, you infer the meaning of the word from these contexts. This is exactly what the distributional hypothesis tells you about it. You can infer the meaning of words from their contexts because, well, basically there is not much more to infer it from, right? Words are things that go together and compose into a meaning. So distributed word representations attempt to capture this meaning by trying to take, let me move to a picture, by trying to take a local context of a word. For instance, in the CBAO architecture, the continuous bag of words architecture, what you have is a very simple model that takes the local context of a word, so basically it's neighboring words, like 5 words on the left and 5 words on the right, and tries to predict this word, okay? So we try to predict which word goes well into this short local window. Or we can do it vice versa with the skip-gram architecture. You take the word, and from the word, you try to predict its context. So you predict the context words from the word itself. Basically, same thing, same idea. So the word-to-vec model is very, very simple again. It's not a deep model, by the way. It can be thought of as just a shallow neural network, just a regular one hidden layer neural network. On the input, you have the word representations. Then the hidden layer is basically the matrix of these word embeddings. And the output layer is an estimate for the word in the middle of a window, right? So what is the idea here? The idea is that in, say, regular natural language processing, when you try to when you try to have a textual input, you usually represent it text as a sequence of words, and we will do the same here. But for each word, you represented it in the form of a one-hot representation, right? So in, say, classical natural language processing, you had each word was a vector of all zeros and a single one, and the size of the vector was the size of the vocabulary, and then you did lots of interesting things about it. But naturally, this representation loses a lot of information. When we read the text, we know that some words are connected with each other. We know that they have some kind of semantic relationships with each other. And of course, we would like to have a representation that does not treat every word as a completely different, completely independent entity, but we would like to have a representation that somehow already captures the intuition behind natural language, right? So like the words, I don't know, what would be here? The word vector and dimension are somehow similar, right? They come from the same semantic cluster. And maybe we would like to have this information because we as humans, when we read the text, we do have this information. We have the experience of reading all the previous texts that we have encountered, and we can use it to understand a new text much, much, much better, right? So, so this is exactly what's happening here. We try to learn a distributed representation. That is, we try to, for every word, we try to learn a vector of just real numbers, like 200, 300 real numbers, that will hopefully have some capture some semantic relationships in this Euclidean space of dimension 200 or 300. So, yeah, I don't know. I think I will skip the mathematics here because it's not really important here. The important thing is that as we train the model, for each vector we get for each word we get a vector, and we get what is called the context vector. The context vector is also a vector representation for the word, but we use basically we use the W vectors when we are speaking about the word as a central word in a window, and we speak of the tilde W vectors when we speak of words in the context. And since I skipped the math, I will not ask you the question of why we need to separate the vectors. But basically, the idea is that we would like to predict the new vector. We would like to predict something by just the scalar product between the distributed representations. And if we had the same vectors, then for most words, they do not really appear in their own windows, right? For most words, it is a very low probability that the word will be repeated immediately, right? So for most words, we would have this optimization problem to try to minimize just their norm and reduce these vectors to 0, which is, of course, not what we would like to have. So this is why we have to have separate vectors for the context and for the word itself. So anyway, at this point, I think I will try to have a live demo of this. The demo will be in Russian. This is a talk mostly intended for the Russian audience, for a Russian-speaking audience. So I apologize in advance for this. All the examples will be in Russian, and I think one of the main points will be how to best use these things for the Russian language. So sorry. Yeah, all right, so we will have a live demo in a moment. Let me just, so that you don't completely forget about me, let's just move on to the next slide. So next we can use these word vectors, right? How do we use them once we have them? Well, for instance, we can plug them into a recurrent neural network. For example, for example, this is a very simple example of how you can use the word vectors. Suppose you want to have a sentiment analysis model, right? You want to predict the sentiment of a short piece of text. How do you do that? Well, you take your text, you split it into words. For each word, you take its vector, and you plug this vector into a network of LSTMs. The LSTMs here basically do language modeling. The purpose of the recurrent network is to predict the next word of the text given the previous words, right? So capture the current state of the statement and predict the next words. And then when you get to the end of your text, you have a hidden state of this recurrent network, and based on the hidden state, you can try to predict the sentiment. Or which is actually usually better in practice, you can take all of the hidden states, then add them up, take the average, or can maybe concatenate them and use them to predict the sentiment label. Both approaches work, and actually, maybe that's a little bit surprising given how simple all this is, but this is a very, very good way to have sentiment analysis. So this is, despite its simplicity, if you do this right, you can have this quality of sentiment prediction basically on par with the best existing models. It is it's worse only than the special recursive neural networks, which I will speak about in a moment. And now we are having some feedback. So this is a very, very simple demo. I just wanted to show you the properties of these word vectors. I will not write any programs. I have trained a word-to-vec model, a very simple, again, this just a basic word embedding model, on a recent dump of the Russian Wikipedia. Okay, so feedback? Yeah. Well, all right. This is no. Okay, we'll leave with the echo. And basically, all I want you to do is to try and give me interesting examples of words for which you would like to see their nearest neighbors. Ah, I see. Okay, this is the Skype talking. Yeah, just a moment. Okay, yeah, okay. Right. So just to get you started, the model has a method which is called most similar, and it basically just searches for the nearest neighbors in the vector space. Okay. So this we will see the words whose vectors are the nearest to the vector of the bigram Научная конференция, research conference. And it kind of works, right? So this is a model where I first mined the bigrams, then the trigrams, and yeah, I stopped at the trigrams, I think. And the trigrams, so you will see some trigrams and bigrams here too. Let me take suggestions from the audience. Which words should I try to search for? Come on, don't be shy. Can I get a word? Oh, excellent. Somebody has been to my talks. I don't think we will see anything interesting. So let's see the word programmist first, software developer, software engineer. And we have some pretty reasonable nearest neighbors like разработчик, аналитик, ведущий разработчик, etc. And yeah, so the request was for the word программистка, which is a female software engineer. So software engineer. Yeah, and of course it's not in the vocabulary. That is expected because it's not a bad thing, by the way. Female software engineers are called программисты also. So yeah, in Wikipedia you will not have this words like программистка or I don't know. So let's hear some other suggestions. But yes, if you train a word-to-vec model on something like I don't know, modern corpus of literature, corpus of news texts, etc., then you will see very interesting stuff about these relations between male and female terms in languages that have these male and female terms. So yeah, word embeddings are sexists. Yeah, yeah. Anything else? Trump. Trump. Love. Okay. Which one's first? I think Trump. Okay, there we go. This is Trump, as in Donald Trump, but the nearest neighbors, okay, we have Donald Trump right here, the bigram, and we will search for that. But here, I think this just says that this is more about the Trump Tower, Trump hotels, etc., about the Trump empire than the person. So let's try Donald Trump. Okay, there we go. So Donald Trump, by the Russian Wikipedia, which I downloaded, of course, before he became president, already has the nearest neighbors of many US presidents like George Bush, Bill Clinton, Ronald Reagan here. Okay, the next suggestion was love. Let's try that. I think we will see something interesting here. Yeah, there we go. So this is another very important property of the word vectors. Okay, you can try to look for some deeper meaning here, but actually, what is important to understand about them? This is important for specific applications too. If you ever use word2vec in practice, you should understand this. That similar vectors are not synonyms. Okay, I think I have a nice example here. If you look, no, we don't. Sorry, no, the Wikipedia doesn't have a good example for synonyms. But yeah, if I had a more extensive corpus, then one of the nearest neighbors for the word synonym would be the word antonym. And why is that? Because word2vec does not, of course, understand the meaning, right? It tries to predict the vectors that are similar in the geometric, in the Euclidean space, are vectors that go together in the same short local windows, right? So, for instance, all emotions will be kind of similar, because they go together in windows about, I feel that and this and that, right? Or John felt this for somebody, right? And so, of course, it will not distinguish positive emotions from negative ones, because, well, kind of, but not really, right? Okay, anything else? St. Petersburg, excellent idea. Let's see if it's. I'm not sure about the hyphen. What's going to happen? No, the hyphens are not here. Is it a bigram? Yeah, it's a bigram. So this is boring, right? These are just Russian cities. Right. Selfie. Okay, let's try it. No, not really. This is probably a rather uncommon word in Wikipedia. So for rare words, you get worse vectors, and that capture less semantics, of course. Okay, and there is one more. Yeah.
Could you repeat, please, what the scores mean?
The scores. Oh, this is just a similarity. I think it's just the scalar product of the vectors. So the cosine distance between the vectors in the Euclidean space. There is one more thing that we can do right now, is to try to see the linear relations between the words. And this is also a very interesting thing, that not only similar words have similar semantics, but also in the word2vec, in the embedding space, you start to have interesting, very simple, but semantic relations between the words. So let me just show you how it works, and then we can try your suggestions. I will do the following. Yeah. Sorry. I'll do the following. Let's try to have Moscow. I'm not sure whether it will work, but let's try to have to see a linear relation between the vectors. So we will take the vector for Moscow. We will add the vector for, I don't know, France. And we will subtract the vector for what? For what do we subtract the vector? For Russia. So basically, I'm asking the model the following question. What happens if I take the word for Moscow, add the vector for France, and subtract the vector for Russia? So what relates to France in the same way as Moscow relates to Russia, right? If you imagine this, it's like Moscow minus Russia equals something minus friends. What is the something? And let's hope it works. I'm not sure. Yeah, there we go. And we see that the model, by doing this just plain addition and subtraction in the vector space, we captured a semantic relation of being the capital of, right? Because basically we have Paris, this is Paris, France, and only then you have something else. Okay. So, yeah.
What if change Moskva for Kaluga?
For Kaluga. Okay, let's. So this was being the capital of. Let's change it to some other city, a smaller city. Let's see whether it works. Yeah. Well, kind of. So, yeah, I don't know what's so similar between Amiens and Kaluga, but Amiens is in France, yeah.
What if we change it to balalaika?
Balalaika. Okay. Let's try that. Well, kinda again. I mean, Lully is a French composer, right? So, yeah, kinda works. Anything else? We don't. It doesn't have to be countries. We can try to do other relations too.
А этот пример с программистом и программисткой. То есть программист мужчина и программист.
Okay. Let's try that. Yeah. Okay. Let's try to search for sexism here. So let's take the software engineer, add a woman, and subtract a man. What's going to happen? Actually, I don't know what's going to happen. Nothing interesting, really. Let's try something else. Let's try ученый. There we go. Okay. I think we are onto something. Let's try mathematician. Yeah, there we go. So that's a great example for this conference. A female mathematician, by Russian Wikipedia data, is a linguist, philologist.
Something abstract like Moscow plus France and minus Russia.
Moscow, but we just tried that. We just tried that.
With France.
With France, yeah. We just tried that with France.
Friends, not like France, but friends.
Friends. Like друзья?
Yes.
What's the point? I don't think we're gonna.
Something abstract, really.
Okay. There we go. So I think what this means is that Moscow and Russia are kind of similar vectors. So when you subtract one from the other, you get a relatively small vector, and you do not leave the neighborhood of friends. So we just get some kind of a synonym for friends. Okay. Anything else? There won't be any more live demos, so take your chance while. Don't waste your chance here. All right. Then let's proceed. Right, so now we have these word vectors, and we have seen some really, really amazing things about them. The amazing, the capture of the semantics is not amazing. The amazing thing is that semantic relations become simple geometric relations in this space. So often we have linear relations that actually mean something. This is important. This is kind of unexpected, actually. Okay, but this is only the first step. And once we have this excellent word embeddings for individual words, we can go, as I already said in the beginning, we can go both up and down from the word embeddings. So if we go up, we try to somehow compose the word embeddings into vector representations of sentences, of clauses in sentences, paragraphs, short texts, tweets, etc. Probably you cannot compress the War and Peace into a single vector, right? Maybe you can, but it's going to be a pretty large vector. But what you can do is you can try to find, for instance, here I was looking for vectors for bigrams, right? And of course, you can try to look for vectors for short texts. So this is one direction. And the other direction is to try and get down from the level of the words to the level of individual characters. Because when we look at the word, we immediately recognize its root, we recognize some of its morphological structure, and we get a lot of the meaning from the structure of the word. They are not individual, independent entities for us. So maybe we can try to make a computer understand that as well. Okay, so let's first try to go up. Let's try to go from word vectors to text chunk vectors. How do we do that? Well, the very simplest idea is to take the vectors of a text chunk and take the average, or take the sum of the vectors. So just do some simple operation on them, reduce them to a single vector. And what, again, maybe an important takeaway point for practice, in practice, it works very well. Okay? So it works unexpectedly well. You take the vectors for words in a tweet or words in a sentence, you simply take the average. And it's pretty reasonable. So it's not the best model around, it's not the best model in the world, but it's pretty reasonable. And when you actually construct a real-life system that tries to do something with sentences, start with just averaging the word vectors. Okay? And this will provide a baseline for you, and this baseline might be hard to beat. Okay? So, and this kind of makes sense because of these linear relationships that we discussed, right? So in this Euclidean space, the semantics is also captured as linear relations between vectors. So it kind of makes sense that when you take the average or take the sum of vectors, you arrive at some meaningful point in the space. But still, it's kind of amazing that it works. Okay. The next idea, which was actually suggested in the original papers on Word2Vec, is to train additional vectors that will capture not the local context, but the global context of a paragraph or of a text chunk. For instance, this is what is called the memory model of paragraph vectors. Okay, and this is from one of the original Tomasz Mikolov's papers. It works as follows. Again, it's based on the continuous back-of-forth architecture. So again, you predict the middle word from its surrounding words in a window. But now, apart from these surrounding words, you also add a separate vector for the paragraph. Okay? And when you take the separate vector for the paragraph, what you have is you have a larger, more global context of the paragraph, right? So for instance, if we had a window like, and then became the king, then naturally we would expect some kind of a king's name inside, right? But we would not know which one, right? But if the global context somehow provided us information that we're talking about, I don't know, France again, then of course Louis would be a much more reasonable, much more expected name here than, say, Karl, who would be expected if we were talking about the Holy Roman Empire, right? So, so global context can improve this word prediction task, and vice versa. By trying to improve the word prediction task, we get vectors of global context that serve the same purpose but relate to the whole, to complete paragraphs. So it works very well. The only problem here is that you have to kind of retrain the Word2Vec model from scratch with these vectors, right? You cannot really just take a prepared Word2Vec model and somehow derive these vectors. You have to retrain this. Yeah, or you can do it vice versa. You can, in the skipgram architecture, you just try to predict words of a paragraph from the paragraph vector. Okay. There are some other ideas, and I think I will not go into details here. There are a number of convolutional, of course, architectures, and there are what is called an interesting idea, what is called a skip thought vector. So in a skipgram, you take a window and cut off the middle word. In a skip thought, you take several sentences and cut off the middle sentence and try to predict the meaning of this middle sentence. All right, but yeah, anyway, I think the the mainstream here is to use the paragraph vectors or just an average of word vectors. Okay, next idea. The next idea of how to combine individual word vectors into text chunk vectors is called recursive neural nets. So this is not the same as recurrent, although the words are kind of similar. And the idea here is as follows. Suppose that together with a sentence, we are given a sparse tree. Okay, so we know how these words go together. We know which word depends on which word. Then we can represent, then basically we can do the following operation. We can try to take, say, two immediately neighboring leaves in this tree and compose a vector for the node above them from the vectors of the words. Okay, and there are some technicalities here, like for every word we have a vector in the matrix, and we multiply the matrix by the other vector and the other matrix by the first vector. But let's just not go into that. Basically, the idea is that we have a single unified function that takes word vectors, word representations, and composes them into the same representation for the node up the parse tree. And it's called recursive because then you apply this recursively for the tree, and you get a single unified representation at the root. Okay? And this idea was proposed by Saussure and a lot of works dating back to 2012, which is ancient history by the standards of deep learning. And since then, it has been, well, basically, what they have been trying to do is to apply this to sentiment analysis. And this is very well suited for sentiment analysis because in sentiment analysis, you can have, for instance, something like very good movie, right? And by all accounts, this is very positive, and yeah, this and the word vectors will be positive, everything will be positive. And then you have a not somewhere, right? Like not a very good movie. And this not should invert the meaning of the whole, well, not the whole sentence, but the whole part of the sentence which is related to this not. Okay, so this is this is like tailor-made for sentiment analysis. This idea, and yeah, there are some variations on this idea. There is what is called the recursive autoencoder, which is the same thing but convolutional. I will not go into detail. And then, of course, you can do it in a deep way. So these were, let's say, shallow recursive networks because they only had this single function. And now we can have deep recursive networks where, again, we apply, yeah, let me just show the picture. We apply, again, some sort of a transformation for the original vectors and get the vector for the node. But now we also have the next layer, and for a next layer, and the next layer takes as input the same layer's previous vectors and the previous layer's vectors here. So this is like a three-dimensional structure. Okay, so this blue node here takes as input the blue nodes on the previous level in the tree, and the corresponding node, but on the previous layer of the network. And again, this is an excellent architecture for sentiment analysis if you have the parse trees. Okay, because composing a parse tree is a problem in itself, as you all know. And all these guys, they do experiments on what is called Stanford Sentiment Tree Bank, where it's a data set where you basically have, it's a data set for sentiment analysis, where you have the already handmade parse trees for every sentence, and I think they are even, they even have supervised information on the sentiment of every node in these parse trees. Like this part of the sentence is positive, but then you have a node and it becomes negative. So if you have this sort of labeling, then of course all of this works very well. But if you start from scratch, if you start from just the text, then you will have to separately solve the problem of constructing parse trees, and it will be imperfect. And you have to have a data set of parse trees, etc., etc. So basically, I don't know how to apply this to Russian, okay? Because I don't have a huge data set of ready-made parse trees that I could use. So for Russian, I don't know. For Russian, recursive networks don't work so far. Okay. So we have gone. So these were some of the ideas of how to compose word vectors into sentence vectors or paragraph vectors. But let us now go in the other direction. Okay. The word vectors were designed to alleviate the problem that you don't want to treat all words as independent entities. But still, when you train word vectors, you treat them as independent entities, right? And sometimes they're just not. And it is obvious that they are not, even without seeing them in context of other words, right? This is especially important for languages like Russian, because Russian and the Romance languages and many other languages in the world have a rich morphology, okay? Because English does not have a rich morphology. It basically, sometimes words have an S at the end, and that's it. And but in Russian, you have very rich morphology. You have lots of what's that in English? How is падеж in English? I am not a linguist. Yeah, cases, yeah. You have lots of cases, and you have lots of word forms, etc. So in Russian, we would certainly like to understand that the words конференция, конференции, конференцией, etc. are kind of similar. We would not want to treat them all as the same word. On the other hand, we would not want to just lemmatize all the words, reduce them to their basic forms, and forget all this morphological information, because this is important. This information is crucial for us to understand the sentence. If you imagine some kind of a sentence without this morphological information, it will lose a lot of the meaning. You will not be able to decipher what was meant, and even if you are, it will be much harder. So you don't want to lose the information, but you want to use it somehow. And the same goes for out-of-vocabulary words. And if you work with, say, user-generated texts like social network posts or tweets or something like that, you will notice that people make typos, of course, and also people introduce some new, what's called occasionalisms, some new words that are that their human human audience understands perfectly, but the computer has never seen this word. So, for instance, for this talk, I made up a word polydistributional. Okay, this word has okay. Now it has a bit more because the slides have gotten around a little bit. But when I first thought of this word, it had 48 results in Google. Okay, which is an absurdly low number. So it was used in one research paper, and in that research paper, it was used. It was not defined in any way. It was just used as something which everybody can understand, and we can. If you look at the word polydistributional, it's obvious what it means, right? It's an adjective that says that something has several distributions. Okay, but unless you have been following my talks, you have never seen this word. It's just impossible that you have seen this word. But you understand it. So we would like a computer to do that as well. And hence, we arrive at the idea of what is called character-level representations. And character-level representations, at first, they try to decompose a word into morphemes. So, like, the linguists know what morphemes make up a word. The linguists have lists of endings and suffixes and prefixes, etc. But again, this adds new errors because you have to have a morphological analyzer somewhere in the loop, and of course it is imperfect as everything. And basically, we just shift the problem from training the character level model to training a good morphology model, but the problem is still there. Okay. So usually now people just started from the characters and they apply some kind of a deep neural network directly on the characters. And it is either a recurrent architecture, usually based on LSTM through GRUs, or it is a convolutional architecture. And then, then usually, I have some a sample picture. This is a typical character level architecture from some paper of 2015. There are plenty of very similar architectures like this. You start with a word. A word is composed of characters. First, represent the characters as one-hot vectors. For characters, you can do it. They are pretty low dimensional. It's just vector of dimension 100 or so. It's okay. And then you plug these one-hot representations into a bidirectional LSTM. A bidirectional LSTM is basically one chain of LSTMs going reading the word left to right, and another reading the word right to left. That's it. And then you, for instance, concatenate their results, and you get the embedding for the word. And then you use it to solve your problems. So what usually happens with these models is you get some kind of a trained model that produces a vector representation for a word. Okay? And so basically this is a different way to get vector representations for words. But now you also have a model that can be used on new words, on unknown words, on words with typos, etc., and it will hopefully produce reasonable approximations to actual vectors. Okay? So now you cannot plug a new word to a trained word to vec model. It will not know what to do with it. This model will. But you can still, of course, have a dictionary and just memorize the most common words so that you don't have to go through this slow model every time. Okay, and another approach along the same lines is used in what is called deep structured semantic models. This is, I will speak about it a bit later. This is a general approach to text processing developed in Microsoft Research lately. And the DSSMs use what is called the letter trigram embeddings on the bottom level. So notice the difference. Previously, we looked at the word cat, and we just read it left to right and right to left, character by character. Now we take the word cat, and we break it up into character trigrams. Okay? So, like, we add this artificial symbol so that every character will have a chance to be in the middle, and we have a three-letter word will be three trigrams. CA, CAT, and AT, what's it called? I forgot. And the wonderful property of this representation is that although your dimension grows, so now the dimension is not 50, as in the case of individual characters, but now the dimension is like, 50 cubed, okay? But 50 cubed is still pretty reasonable. You can work with that. And so it's like 100,000. It's okay. We can manage 100,000 vectors of dimension 100,000. But what is important is that now we can forget the ordering. We can treat this thing as a bag of trigrams. And there will be virtually no collisions at all. In their experiments, they had like a 5 million word dictionary from a huge user-generated corpus. There was a lot of typos, a lot of new words, etc., etc. And they had among 5 million words, they had 22 collisions. So there were 22 cases when 2 different words produced the same bag of trigrams. I think we can live with that. So now you can lose the ordering, and you can just treat this as a single vector where you have ones at positions where the correct trigrams are. And then you can build the model from ground up on this. Okay, and then of course you can have convolutional approaches. I will not go into detail here because it's kind of obvious. You start from local windows on the characters and you generalize them one by one. And to me, it appears that character level models are really important. So especially for languages like Russian. It says Ukrainian because these were slides for AI Ukraine originally. But yeah, for Ukrainians, it's important too. And for Romance languages and for other languages. Okay, and before we move on, if you just, maybe I can mention one more modification of the word vectors. There are works on word embeddings that try to add some kind of external information to word embeddings. Okay, so we have seen that word embeddings automatically produce reasonable semantic relationships between the words. Okay, but in many cases we know these semantic relationships. We have Wikipedia, we have WordNet, we have huge ontologies. We have what's called Freebase, I think. It's a huge database of knowledge base of things like subject, relation, object, like I don't know, Russia has capital Moscow, okay, and there are predefined relations and objects, and they are connected by these relations, and it has billions of these triples. So we already know all these facts. We don't have to derive them from raw text. We can try to add them artificially. So this is what the RC model does. It basically adds a specifically constructed regularizer that tries to make these relations from the ontology, from the knowledge base. It tries to make them as linear relations in the vector space. Okay, so there is a special regularizer that tries to draw the vectors and to make the vectors such that they conform to these kinds of linear relations. Like there should be a vector that corresponds to the relation born at, and say Geoffrey Hinton was born in Wimbledon, London. So the vector for Hinton minus the vector for Wimbledon should be approximately the same as the vector for Leonhard Euler and the vector for Basel, Switzerland, minus the vector for Basel, Switzerland. And of course, it's a huge regularizer. There are some technical problems, and they are solving them in some way. But basically, the idea is that we have lots of external information. We can try to incorporate them into the embeddings too. Okay. Yeah, and one more thing again. Sorry. Yeah, one more thing before we proceed. There is one more problem with word embeddings, and this is the problem of homonyms. Okay. Many words have several different meanings. And not even words that you think of when I say homonyms, like in Russian kosa, that have just completely different meanings. But also, if you just take a regular word, like regular, it has quite different meanings depending on the context, right? Even though there is something vaguely in common among all them, still the meanings are very different. So this is a big problem, actually. And the solution, obviously, would be to have several vectors for each word and to somehow have different meanings and then to choose which vector to use from the context. Okay? But this makes the mathematics and the machine learning part of this much harder. So we have to use some kind of variational approximations. We have to use stochastic variational inference to train the meanings, because the actual vector that is used now now is represented as with a latent variable because we don't know which specific meaning we want to use, and we even don't know how many meanings a word should have. Okay, so this this becomes complicated, but people can do it, and I think, and this is a good place to mention that probably the best current model was done in Russia, in Moscow, by Dmitry Vetrov's group, specifically by Sergey Bartunov. Okay, let's move on. The next part. So we have spoken about word representations and lots of details. Now we will proceed to a brief overview of how the deep learning stuff is used on these representations. What are the architectures? And first, I begin with just very general approaches that can be used for basically any task at all. And usually, a large class of these approaches is based on language modeling. So language modeling is the problem of just predicting the next word in text. Okay, and recurrent networks are pretty good in language modeling. And here again, I think because everybody is falling asleep again, so I think we'll have some fun examples again. This is a very simple model. It's just I don't remember exactly. I think three layers of LSTMs that were trained on a part of Russian Wikipedia. It would be too long to train the whole Wikipedia. A part of Russian Wikipedia to generate text symbol by symbol, character by character. Okay, it does not know about the words. It does not know the word vectors. Does not know anything. It just has a stream of characters. Sometimes there are spaces, of course, but it does not know that it has any specific meaning. And it tries to simply predict the next character in the stream. And then you can ask it to generate a new text. And when you ask it, so you start with some kind of a seed, and then you say, okay, now generate me the next letter, then shift the window, generate the next letter, etc. And you can see that it kind of sort of does something reasonable. So, and this looks very much like absurdistic literature. If you sample with low variance, you have very, very reasonable looking text, but it kind of repeats itself and gets back to the same local minima, to the same part of the search space if you sample with low variance. And this is kind of the luckiest monologue from Waiting for Godot, right? And like if you make the variance in mid-range, you get something reasonably looking. And then if you have high diversity, if you have really high variance in sampling, then you get some new, interesting, but plausibly looking words. Okay, so now you generate character by character, so you can get new words like Карл Унимобщекрипских or Юностариансический, and so on. Excellent. And another fun example, this is approximately the same model trained on a database of Russian poetry called Poroshki. And if you look at this, it's fun. And yeah, I chose the family-friendly examples. But the interesting part here is that from a stream of characters, yes, there were, of course, new line characters in there, but from a stream of characters, it kind of understood the rhythm of poetry. So it kind of almost works. Sometimes it makes errors in, I don't know the English again. What's English for ударение? Stress. Stress, okay, thank you. Sometimes it makes errors in stress, in long words. So then the rhythm is broken. But you can always understand where the error is. So you can always kind of, shift the stress and see what it meant, what it was trying to say. But it works, okay? And it's really, it kind of works, yeah. Okay, so this is very interesting. And this is just a slide where I wanted to show a relatively common modern convolution architecture for processing. So for instance, here, what we have is we start with characters, we concatenate the embeddings of characters, then we take multiple levels of convolutions on these characters, on this and max pooling, then we concatenate the results, we pass them through what is called a highway network. I will not go into detail about this, what that is, but that is also a network that tries to pass the gradients through without any obstacle. And then it goes to a recurrent net. This is a sequence of LSTMs. And then from these LSTMs, we get the outputs, and some very simple last layer predicts what we are trying to say, what we are trying to do, the target variable. So this is like an end-to-end architecture. And an important point here is that usually it is trained entirely end-to-end from the beginning to end. There is no unsupervised pre-training here usually. You just take your data set and you train the whole thing. Okay? Or maybe you start, for instance, with existing word vectors that have been trained on a huge data set and you cannot replicate that. But then you still plug them into your model and you fine-tune the vectors to your specific text corpus. This is an important point. You can use predefined word vectors, but it is usually better to fine-tune them on your own data set. Okay, DSSMs. I promised to say a few words about those. DSSMs, I will not go into a lot of detail about their architecture. Okay, basically it's just a series of convolutional layers. There are some tricks, but basically it's just a deep convolutional network. And the interesting part is that they made it work so that it basically can do anything with a text that has a supervised labeled data set. So if you know your target variables, like in sentiment analysis or in, I don't know, named entity recognition or some sort of this kind of problem, you can train this whole architecture, again, end-to-end, starting from the trigram embeddings that I explained, and it works. It kind of works. And an interesting specific application here is that you can try to capture the similarity between texts, right? So you can use this network twice and try to, for instance, if you have a database of paraphrases, coming back to the conference topic, I think, if you have a data set of paraphrases, then you can try to make these hidden layer representations, these top layer representations, similar, more similar for actually paraphrases and less similar, pull them further apart for non-paraphrases, okay? And this also kind of works. I will skip this. But I just wanted to mention one specific application. You can also, when I said that you can try to capture semantic similarity, what the applications that they actually had in mind and the mainstream application of this thing is semantic search. Okay? So now suppose that one of the texts is a query and another text is a document. And you try to capture the semantics, and the semantic similarity basically now means relevance. Right? So how relevant this document is to this query. And suddenly, when you reframe the problem like this, you have huge data sets, right? Search engines have huge data sets of relevant and irrelevant documents. And you can train this kind of architecture. And it started at Bing, at Microsoft Research. But I think, again, this is, I think, an illustration of how rapidly developing all this stuff is. On a couple of weeks, a week ago, Yandex published a post where they explained how they use a slightly modified, yes, an improved DSSM architecture in their new pilot search engine, okay, which is doing exactly this, which is looking for semantic similarity between queries and documents. Okay, I will skip this. This is an amazed Lisa doll losing to AlphaGo. But yeah, I'll just mention that you can also use deep reinforcement learning to generate text. This is very exciting, but we will not have time to go into the reinforcement learning also. Okay, and now in the final part of my talk, I will just show you a few examples of specific problems and what specific deep architectures are used for these problems. First problem is dependency parsing. I think I will not go into detail here. Again, this is not, I don't want to make this into a very technical talk. But the basic idea is that you remember that we mentioned parse trees and that it would be very useful if you had a good model to construct parse trees. So how do we construct parse trees with the magic of deep learning? Well, it turns out that to construct them with deep learning, you have to first remember how they're constructed with classical algorithms. So the classical dependency parsing algorithm has a stack, and it has some kind of a rule to select the next, to push and pop tokens from the stack and unite them into the parse tree. Okay? And this is exactly what we are trying to model with the neural network. So there is some kind of a stack, and the neural nets are modeling these decision rules for which tokens to push on the stack, pop from the stack, how to unite them, etc. And we can train this. So basically, we have a buffer, we have a stack, and we have a list of actions that the parser can take and has already taken. And they are all modeled by LSTMs with stack pointers. So they are all modeled by recurrent architectures that look inside the stack and can make decisions based on what's in the stack and in what order. No details here. I'll skip that. OK, and now to the really interesting stuff. The really exciting models, I think, for machine translation, dialogue models, and question answering. And this will be the last 3 topics of my talk. Probably the most ambitious problems of natural language processing, at least for now. So the first short remark about this is that there is always the problem for evaluation. Okay? For instance, in machine translation, when you produce a translation of a text, yes, you usually have some sort of parallel corpus where for each phrase you already have a good translation. But now you have obtained a different translation. And it is very non-trivial to to evaluate how good this translation is. Okay, so this to do this perfectly would require again to have a perfect translator. So this is a problem, but this slide basically says that people have ways to work around this problem. Okay, so you can in models that have to produce actual text, there is a hard problem of evaluation, but people have some approximations to it. So they have actually some sort of quantifiable metrics that can tell you how good your translation is. Well, not really how good, but how similar it is to the perfect reference translation that you have. Okay, so with this in mind, let's proceed. Machine translation. Translation is a very good, very interesting problem for machine learning for 3 reasons. One, it's very practical. I mean, it is no problem to explain why machine translation is important, right? Unlike generating random text from Wikipedia. And by the way, an interesting historical fact, the first, what is called winter of artificial intelligence was, which was a period in the early 70s, I think, in the late 60s, early 70s, when people got discouraged in artificial intelligence and specifically neural networks. It was, in many respects, caused by a failure of a machine translation project. There was a huge machine translation project based on some Cold War stuff. Basically, the American military was trying to create a system that would automatically translate Russian documents, and they failed, of course. Nobody could do it in the 60s. So the conclusion was that all this stuff doesn't work, and it takes longer, it's more expensive, and it's worse than human translation. So basically, let's forget about all this artificial intelligence stuff. So machine translation is very practical, very important. On the other hand, it is very high level. I would argue that, I mean, probably I will be proven wrong. But for now, I don't see how you can have a perfect translation machine without at the same time understanding the text, like real, true understanding. And on the third hand, as I said, it's quantifiable. So even though it is very high level, we do have a way to evaluate the results. And this is also very important. So machine translation is a very, and we have large available data sets. We have huge parallel corpora of texts, at least for the popular languages. So what do people do? How does machine translation work? I'll skip this one. So basically, the first idea would be to try to take the classical statistical machine translation. What is classical statistical machine translation? We take a sequence of words and we try to predict the next word given the previous words and, of course, the thing that we are trying to translate, right? And this is how we generate the words in the translation one by one. And this is exactly how recurrent networks are used for language modeling without any translation. So it would be very natural to try to apply the same idea to machine translation too. And this is one of early 2014 early architectures for deep machine translation, and it worked like this: you have the input text, you put it through bidirectional LSTMs, and then you take the result, and the result goes as a condition, as one of the inputs, into the thing that generates words by one. Okay? And it kind of worked. It produced state-of-the-art results. But then, very soon, it was improved. And the improvement came from what is called encoder-decoder architectures. And this is, again, an important, interesting, new kind of architecture that basically was produced by the needs of natural language processing. This is an important point here. What is an encoder-decoder architecture? We take the input sentence. Let me just restrict this to models that translate one sentence. So we take the input sentence, then we put it through some kind of a network, usually a recurrent network, and we combine, that's okay, and we, and we combine this all into a single vector, okay? And then we decode the vector into the translation. So we first encode it into a single state, which somehow should capture the meaning, and then we decode the meaning back. So this worked, kind of. And then it worked even better when people added what is called attention. An attention mechanism. Attention mechanism, basically, it's a separate small neural network that tries to tell you which part of the sentence we are currently translating. Where specifically we should look to translate this current word. This is very, again, it's a very simple but very rich idea that has many applications in also image processing. You can do attention on images, etc., etc. But it also improved translation. Okay, and the thing I wanted to mention about machine translation, again, the field is developing very rapidly. A very recent work, September 26 this year, I think a very important work that basically explains how Google Translate works. Okay, so this is a paper from Google, which is called Google's Neural Machine Translation System, and it basically explains the how it actually works for Google Translate. And it turns out that it works in exactly the same way. Okay, so the paper does introduce quite a few interesting tricks. I will not go into them, but basically what is important to see here is that it is exactly the same architecture. It's an encoder and decoder architecture with attention. Only they made it deeper. They had more layers. They had special tricks that make the deep recurrent network work, which is non-trivial. And they have also a few more tricks which I will not speak about, but basically it's the same encoder-decoder attention architecture. So in the field of deep learning, what you have is that there is a very small distance from what is actually practically working for the largest corporations in the most widely available practical solutions and what is happening in the academic community. So you basically have a paper on this with some artificial experiments, and then half a year goes by, and you have the same architecture in Google Translate. Okay. Yeah, I'll skip that. I'm running out of time. So I think I will skip the dialogue and conversation because it is basically the same idea. Again, you have an encoder for the input utterance, and then the hidden state and the context from the previous conversation goes into a decoder that produces your utterance. And the dialogue goes like this. So it's kind of easy. But what I do want to finish with is question answering. Question answering is a very, very interesting problem again, because first you, again, it's easy. It's obviously supervised. You can ask questions with known answers, and you can obviously collect relatively large data sets. But the interesting part here is that computers are very, very bad at question answering. They are very bad at understanding. And if you look at the actual examples of the current question answering data set, you will see that that they are very trivial for humans, right? So the questions are like, I don't know, Mary went to the bathroom, John moved to the hallway, Mary traveled to the office, where is Mary? You have to answer office. And it is hard for a computer. So the problem here is that while a computer is pretty good at understanding the relationships between words, here sometimes in questions you have to reason about the world around us. And of course, the neural models have no understanding of the world around us. They just manipulate strings of vectors and strings of symbols. So it's hard for them to understand this stuff. And it becomes even harder when you add something like basic deduction, like sheep are afraid of wolves, Gertrude is a sheep, what is Gertrude afraid of? Okay? It seems like exactly the kind of problem where a computer should be good at, like it's logic, but no. It's very hard to recognize that this is simple logic. So what people actually do is they do some kind of a memory network. And this is, and I will not go into detail on how they work, but this is a very rapidly growing field where basically you have models. Let me just show, let me show a picture like this. You have models where you have a memory, and then the neural networks try to learn how to operate this memory. So not in this model, but in another model, you basically, the output of your neural network is just a vector that is interpreted as a command, like take this pointer at the memory and take the value from there, or put this value there. So you try to learn a network that produces commands to a memory. And yeah, it kind of works, but it still works very, very poorly. And what I want to finish with is this. A Russian intellectual game, Что, где, когда, which you have probably heard about. And if you're Russian, of course. If you're Russian, you have heard about it. So in this game, I mean, you've probably heard about this game on television, where it looks like this. But in reality, it usually looks like this. There is a hobby version of Что, где, когда, where people just compete with each other in answering interesting questions, and whoever answers the most wins. Okay. And what is important now to understand is that over the years, it's been like 30 years of Что, где, когда, over the years, people have collected a large database of questions. There is a database of about 300,000 questions, which is much, much larger than the databases of questions like the one I just showed. But of course, for now, these questions are hopelessly hard for computers. So let me try those on you. These are what is called своя игра, which is basically Jeopardy, but compared to Jeopardy, it has more. I mean, it has less direct questions. It's not just trivia. Usually, you have to apply some kind of I don't know, induction to get it. For instance, who can answer this question? What is the year when the topic is Russia in the beginning of the 20th century, and the question is, in which year did Russia collect 5.3 billion, what's that in English? Okay. Yeah, 5.3 times 16 million tons of grain. What was the year? В каком году собрали 5,3 миллиарда пудов черновых? Какие есть варианты? Тема России в начале 20 века. В 13-м, конечно. Of course, the answer is 1913. But to get this answer, you have to sort of understand the whole context of Russian history. You have to understand that throughout the whole Soviet period, there was a common thread of comparing the industrial successes with the year 1913. So if they are asking about some kind of a statistic from the beginning of the 20th century, then it kind of makes sense that it's about 1913. But how can a computer do that? I don't know. And I think the last slide I will leave you, and this is Jeopardy. So these are questions that supposedly do not require too hard, collective cognition. And here I will just leave you with a few examples of actual что, где, когда questions. Just if possible, let's leave this slide on, just so that your gestalt won't close, and you can think about them over lunch. Okay, thank you.